Number 2 in our practice exam is a conceptual problem concerning this reaction coordinate diagram. Chemical kinetics is the topic here, and so we want to take a look at our parts of this question. And so looking at it, how many intermediates are represented. And so whenever we start looking at these, we're going to see that we begin and end with reactants, and we end, like we said, with products. Sorry, we begin with reactants, we end with products. And so the other values in our plot are intermediates. So I'm just looking for, after I've identified the reactants and I've identified the products here at the beginning and end, those are technically in valleys of our reaction coordinate diagram, our potential energy diagram. And our other valleys here are going to be intermediate structures. So 4 structures through this mechanism, and 2 are going to be intermediates. 2 represented intermediates in our diagram. We're looking for the valleys here. There's the valleys right there, 1 and 2, with the reactant and product technically being in valleys themselves, depending on how advanced your class covers, but we can just look at those as beginning and ending, and then intermediates in those middle 2 valleys. Is the reaction endothermic or exothermic? And so when we have the product being more stable, the product has a lower energy, than the reactant, so we're going to have a negative enthalpy of reaction. Okay, so that negative enthalpy of reaction is going to mean that we are exothermic. Heat is released when we have a negative, a more stable product than the reactant. So we see this is negative 15 kilojoules per mole, and then negative 10 kilojoules per mole for the reactant. So a lower number on the number line for the product gives us exothermic reaction. The mechanism of the reaction consists of how many steps, so we can always tell by how many transition states there are. Each reaction step has a transition state unique to that step. These are going to be peaks. So we've got peaks and valleys. Our transition state are going to be the peaks here, with our intermediates being the valleys in our structure. So 3 different peaks going over to the high energy point, the point where the bonds are stretched to their max, the most unstable form that the intermediates and the reactants are going to be in before they combine to form the next structure. And so we see 3 of those, 3 transition states. 1 little double plus sign for a transition state, 1, 2, and 3 for those. So we have 3 total. 3 steps, 3 transition states. Part 4, we want to calculate the activation energy of the first step. And so that's essentially the distance between the reactant energy and the top of a peak. So there's that first step. There's the activation energy. The energy it takes to get over the hill is measured from the reactant line all the way up to the peak. And so for this one, that is plus 10. The energy of the final state, the transition state energy minus the reactant energy. And so that's the delta. Let me put it in terms of enthalpy. Enthalpy of the transition state minus the enthalpy of the reactant. And so that's going to be plus 10 from the number line. There's plus 10 right there, equal to the top of the state there, plus 10 minus negative 10 for a total, minus 10 there. That double negative makes a plus. We end up with plus 20, and our units are kilojoules, or kilojoules per mole. Plus 20 there. So 10 minus a negative 10 gives us 20 total units across the number line. What's the enthalpy of reaction? Well, it's the products. Delta H of the reaction equals the enthalpy of the products minus the enthalpy of the reactants. And so what we end up with is a negative 15 minus a negative 10. So that gives us negative 15 plus 10, or negative 5 kilojoules overall. That's pretty good because we predicted it was an exothermic by inspection earlier. We see that we do indeed get a negative 5 kilojoules. Okay, and we should show our work in the box there, so make sure that ended up in the box in your final answer.